Welcome back to part 2 of memory diagrams and activation records. In part 1 we covered the rules of scope as well as the different types of memory available to a program. In this, part 2 of 2, we'll get to what you've all been waiting for. Memory diagrams. So without further delay, let's pick up where we left off in the course workbook. Now that we have a grasp of the different types of memory, we can proceed by studying activation records. An activation record records all of the functions which are active at any point in a program's execution. Activation records are sometimes called memory diagrams because they clearly show what memory is being used at any point in the program's execution. As a gentle introduction to activation records, we can consider call graphs. A call graph records which functions call which other functions as the program executes. In this example, we can see that main calls function 1, and function 1 then calls function 2, and function 2 finally calls printf. Depending on the level of detail you want, you may or may not want to include any standard libraries in your call graph. If we only include main and user-defined functions, function 1 and function 2, we can sketch out the following call graph. In the call graph, main is always the parent or the root of the graph, and there will be one arrow extending from each function for each function that it calls. For example, main calls function 1 and function 2, and it has 2 arrows extending from it. Now, take a second to answer the questions given in the workbook. What functions are active or have activation records at point 1? And what functions are active at point 2? At point 1, this may be a trick question as well, since point 1 is actually reached twice during the program's execution. The first time is through function 1, which then calls function 2. In that case, function 1, function 2, and main are all active. The second time that point 1 is reached is when main calls function 2 directly, in which case only function 2 and main are active. At point 2, the call to function 1 has completed, so only main is active. Now I'm going to show you what an activation record looks like when we draw it. I will draw it for the first time that point 1 is reached. So we have main, function 1, and function 2 all active. Here is how you will learn to draw activation records. Activation records clearly indicate the 3 different regions of memory: static, stack, and heap. The example program doesn't have any dynamically allocated memory, so the heap is empty. There is one string literal being used as a type specifier in the printf function. The memory for string literals appears in the static section. Most of the memory that's being used is on the stack, or the automatically allocated memory. Each function has its own activation record: main, fun1, and fun2. The activation record for each function is divided into 2 sections: local variables on the top and arguments on the bottom. So for example, the activation record for function 2 has local variable z on top and function argument variable k on the bottom. That will be our convention for the course, to put locals on top and arguments on the bottom. If a function doesn't have any local variables, such as fun1, we'll put the label noLocal in the local variable section of the function's activation record. Similarly, if a function, such as main in this example, doesn't have any arguments, we'll put the label noArgs in the argument section of the activation record. If one of the sections of memory doesn't have any allocation, for example the heap in this example, it is not necessary to show it. However, you may prefer to indicate all 3 sections so you don't forget any of them. One final thing to note is that The stack section grows upward from bottom to top. This is the same idea as stacking blocks or pancakes on top of one another. The most recently called function is on top, and the earliest function is on the bottom. This next section states our conventions for activation records. The activation record for each function is divided into two regions, the upper region for locals, lower region for arguments. Only draw activation records for active functions, and the activation record for main will always be on the bottom of the stack. The terms for adding an item to a stack and taking an item off the stack are push and pop. You should understand what is meant if someone says a function has been pushed onto the stack or popped off the stack. With this next example in section 8.9, take a few minutes and try to draw the activation records for each of the 4 points, keeping in mind the conventions that we just established. Welcome back. In approaching this problem, you'll notice that there is only one function, main, which means that you only have one activation record at each point. To decide which variables to include in the activation record, you need to remember the rules of scope. The comments in the source code help you to understand the scope or the lifetime of each variable. As with the previous example, there is no dynamic allocation, so it's not necessary to draw the heap. There is, however, two string literals in the cout expression. X has a value of and a \n. Technically, those would be allocated on the static section, but for now, if you only drew the stack, that'll work just fine. Here's the solution for the activation records at each point. I've only drawn the stack for each one. Main doesn't accept any arguments, so the bottom half of the activation records always show no args. The local variable section is more interesting. At point 1, only x has been declared, and so only x appears in the local variable section of point 1. At point 2, we are in the scope of the variable a, and just like for functions we drew the most recent function on top, we also draw the most recent variable on top, so a appears above the variable x. Notice that the value of x has changed due to the increment x plus equals a. At point 3, we're in the scope of variable b, and since b is the most recently declared variable, it appears on top of our stack now. And finally, at point 4, the variables a and b are both out of scope because we're now past the ending brace for that scope block. But before we left the scope, x incremented its value by b, so the new value of x is now 11 plus 9, 20. As a side note, local variables should always be defined at the top of a block inside of a C program. Now this is a C++ function, so it's okay to have int b declared after the variable a in the same scope was used. However, the standard for C language states that all variables should be declared at the beginning of a block, which would mean that int a and int b would both be declared before the increment x plus equals a. Some compilers will give error messages in these situations. In the next section, I'm going to discuss a different way of drawing memory diagrams using memory addresses. If we consider the same example as before, the activation record can include a memory address for each variable. That memory address will be given to you in an exam situation. Just for the sake of this example, I've used an address of 4000 for the variable x. At point 2, the variable a has entered into scope. Now the memory location of variable x was arbitrary, but once we set that location, we can decide what the location of variable a is. Can you guess why the difference between the two addresses is 4? Variable a is an integer, and we've shown that variable a is an integer, and we're assuming that integers have a size of 4. That explains why the address location differs by 4. The stack will grow in a continuous fashion without any gaps. That explains why the difference isn't larger than 4. For example, whether the addresses increase or decrease is a convention. In this course, we'll say that addresses decrease as we add on to the stack. Finally, we have one last example of activation records taken from the textbook. In the example in Figure 5.7, this example uses slightly different conventions than we do, so don't worry about the exact details here. One thing you'll notice is that they've allocated memory for the return variable with the label return location R1. Return location is necessary since main returns an integer, but we won't concern us. In Figure 5.8, you can observe that the activation record for square has been pushed onto the stack. Now that you've completed the 2-part series on memory diagrams and activation records, you are familiar with the rules and conventions that we'll use for drawing memory diagrams. Remember that only active functions get an activation record. Keep in mind that you don't have to draw all 3 regions of memory if some of them are empty, but it's always a good idea to at least recall the 3 to make sure you aren't forgetting something. Remember the rules of scope, and if a variable has gone out of scope, make sure it doesn't appear on your memory diagram. And as a sampling of the conventions that we have, remember that we decided to grow our stacks upwards, and that memory addresses decrease as more items get pushed on the stack. You now have all the knowledge you need to work through tutorial number 1, which is located near the end of your workbook. Please attempt to work through the problem on your own, and I'll be posting a solution online for you to check your answers. In the tutorial scheduled on May 21st, Tuesday, we'll be going through tutorial number 2 and a little bit more about pointers. Wednesday at 2:30 will be the deadline for quiz number 2, which covers the topics included in this presentation as well as the past 3 other presentations. If any questions come up during your preparation, feel free to email me or post to the discussion board.